Ah, a new. Look how confused they are. New atoms are a tad bit stupid. They usually don't know what they are. So this might be a good show. His protons haven't settled yet, so his nucleus might be a bit upset. Not yet as dense and positive as they should be. But he did better than his brothers and sisters, so I don't think he'll fall apart. He might be a little dumber than the rest.
Can you shut up? Why do you keep talking? And why do you keep talking about how my nucleus is positively charged with protons and neutrons?
How rude! Where are your parents? Other atoms like you. Duh. Where is that example when you need her? I'm here to watch a show, not babysit.
I don't need to be babysat.
Shut up! Go count your electrons or something while I find that dang silicon.
Electron?
The negative particles that take up the space around your nucleus.
Can you shut up? I was so close.
Man, this is great.
83 electrons. Silicon, you are a real jerk.
I didn't ask to be stuck up here my entire life explaining to a bunch of new atoms what a mass spectrometer is. I especially didn't want a bismuth. I mean, look at them. They're such babies. When? Who are all these other isotopes? Who am I? Where am I?
You know you're actually not funny.
Oh my god, could you please be quiet? I was at 15.
My gosh, not only is he dumber than dirt, he's an airhead.
Silicon, stop bullying.
Fine. Hey, I bet you want to know what those isotopes around you are, huh? Yeah, they're basically your brothers and sisters. You all have the same protons. You were just the only one stable enough to survive. Okay, that doesn't matter much. The only thing that really matters is that you are the only one who survived, so you have 100% abundance. That means that your relative atomic mass is just your mass, because you're the only one who exists. You got that? Whatever. My job is to send you off to your family, not to make you understand. Do you remember?
But what am I?
Were you not listening? You are a bismuth atom from the bismuth family. You have 83 protons and electrons, and your relative atomic mass is 208.98 AMU. Can you remember that?
Yeah.
Are you serious? Here. Just take this. Atomic number, family name, atomic mass. You got that?
Where do I...
My job is not to explain everything to you. It's to find your family. Go bother helium or something.
Where do I...
Over there. Now leave me alone.
Hello? Are you my family? I know you can hear me.
Keep the perimeter. You failure of a medal. I presume Silicon sent you? That lazy criminal always wanting me to do her job. Well, go to hydrogen. My flouncy cousin loves playing with idiotic babies like you.
Where?
That way, now leave.
hiking, where will I go? I could fly home with my eyes closed, but it get kinda hard to see the snow.
Miss? Are you my family?
Oh my goodness! You're the new basement! You're so cute! Oh, this won't do. Come along. You're over there! I told you to come along.
How did...
Magic, duh. Silly question. Oh, yes. Here. So, you trying to find your family, huh?
Who are you talking to?
Oh, okay. Yeah. So you're trying to find your family. Well, you're a transition metal, so you live quite a ways away from me.
So what makes me a transition metal?
Well, you only have 2 valence electrons, and you would expect you to have more than that. However, the electrons that you would expect to be valence are actually pushed into lower energy levels because the attraction from the nucleus is greater than the repulsion from the energy level, and that makes you a transition metal.
Energy levels?
Well, energy levels are like a shell where you can usually find the electrons to be. So, I'll need to draw this out for you.
Like a seashell?
No, not really, and don't interrupt. Anyway, you can find a max of 2 electrons on the first shell, and so, here's the nucleus, and here's the 2 electrons. And you can find 8 on the next. And a way to calculate the maximum number of electrons on a level is to hold level can hold is to square the main level number, which is n, and you square that, and then you multiply it times 2.
What are orbitals?
Well, orbitals are a region of space where the electrons are most likely to be found. So, do you want to see the shapes of them? I bet you do. Okay. So, here we have the s orbital. There is only one shape because there's only 2 electrons, and they always flow in opposite directions for any orbital. It doesn't matter. Here's the p orbital. It's kind of like a peanut shape. And here's the d orbital. This is where things start to get funny. You can remember as D as in Daisy. And then you have this funny one with the donut. And then here is the f orbital. This one can hold the most amount of electrons and has the highest energy.
Oh, but how did you get a laptop?
All night, Bismuth. Yeah. This is the 1s orbital, 2s orbital, 2p orbital, 3s orbital, and 3p orbital. Now, don't you remember how many electrons can there be in one orbital box?
2.
Good. Okay. And then chlorine looks like this, doesn't it? Yeah. When filling in the electron configuration, there are 3 rules. Rule number 1, electrons are lazy. They fill the lower orbitals first before going on to the higher orbitals. So you'd fill the 1s orbital before going on to the 2s orbital. And you would expect your valence electrons to fill the outer shell. However, an exception to this Aufbau's principle is the fact that the attraction from the nucleus is greater than the repulsion from the electrons. Do you remember this from earlier? Rule number 2. Electrons repel each other, so they go to other boxes in the same orbital before they pair another. This means that every orbital in a subshell is singularly occupied with 1 electron before any one orbital is doubly occupied. Oh, and all electrons in singly occupied orbitals have the same spin. That takes us to rule number 3. An orbital can only contain 2 electrons, and the 2 electrons must be spinning in opposite directions. You see, in this electron configuration, you see how they're going in opposite directions? You see the arrows in opposite directions? Yeah. And here we can see the electron configurations of the first 36 atoms. And we can also see the exemptions on the bottom of the 2 primary exemptions onto how electron configurations are drawn.
How do you know these?
Orbitals?
Orbitals even exist?
Well, when electrons get excited with energy, they move to higher energy levels, but they fall back down because they lose energy. And when they fall back down, photons of light are emitted.
Okay, but how?
You're interrupting again.
Sorry.
Anyway, there's a spectrum of energy from radio waves to gamma waves, the electromagnetic spectrum. Visible light is there too, from red to violet. Gamma rays have the most energy, so the highest frequency, while radio waves have the lowest frequency, and so they have the longest wavelengths. Frequency and wavelengths, wavelengths are the lengths between spaces between bumps, are inversely related because the more space there are between the waves, the less energy is being radiated. So, for example, radio waves have the longest wavelength, and then for visible light, red light has the longest wavelength and the lowest frequency of light, while the violet has the opposite with the shortest wavelength of light and the highest frequency of light.
Okay, this is interesting and everything, but how does this help me find my family?
I'm getting there. Remember when I told you about the photons? Well, if the color emitted from the electron falling level is blue, it emits more energy than if it glowed red. So it takes more energy to move. Every time an electron falls, it can be seen on the line spectrum.
Ooh. What's the difference between a line and an energy spectrum?
The proper term is the electromagnetic spectrum, but to answer your question, you might just have to look at it. First, the electromagnetic spectrum of visible light is a continuous spectrum. It carries every color within it. A line spectrum just features the colors emitted when an electron falls from an energy level. We can use mine.
Okay, got it.
Here. This is a line spectrum, or my emission spectrum. It is simple, since I only have one electron. The red line is the color emitted whenever an electron falls from the third to the second level. The light blue is from the fourth level, and the indigo is from the fifth level. And the violet is then from the sixth level. This shows that there's discrete energy levels that exist for electrons, since hydrogen atoms like me constantly emit these colors when given different amounts of energy.
Why doesn't it show the color for the energy it takes to fall back to the first energy level?
Well, that takes so much energy that you can no longer see it on the visible light spectrum, but rather the ultraviolet spectrum, which we can't see into that spectrum.
Okay, but what about the seventh?
After the 6 levels, the electron levels converge into the convergence point. No other electrons beyond that point can be attracted to the nucleus, since the nucleus is just so far away, the attraction isn't felt. Also, since it takes so much energy to pull that electron away from the nucleus, the convergence limit is at its highest frequency, which is after the 6th level.
Okay, but how does that help me find...
Oh, 1 second, hold up. Hey, Chlor? Yeah, that sounds fun. No, I'm not doing anything.
I think we should go, Bismuth.
You're still here? Don't you have anything better to do? Are you my family?
No.
Do you know how to find out how many electrons an element?
Sorry, kid. Hydrogen is throwing a party, and I'm not missing it again. Go to 5th Street. That's where a lot of other metals live.
Are you my family?
Definitely not. We might both be shiny, but I have a much higher caliber. Go to Goldilocks over there. They have nothing better to do.
I can hear you.
I know.
Are you my family?
Get lost.
Jeez, these precious metals are as bad as the noble gases.
Is your only purpose to comment on my life, or are you gonna help?
Wrong way!
Please tell me you're my family.
Do I look like a bismuth atom to you, kid?
Yes?
No.
I don't know. God, nobody ever tells me anything. They just keep talking about orbital whatevers, and I don't know how to find how many electrons there are, and nobody just tells me where my family is.
Well, it gets easier the older you get, kid. But it basically, you can tell by the energy it takes to get you excited.
Excited?
Like when your skin starts expanding and you start changing colors.
That sounds terrible.
Don't worry, that only happens when you get set on fire or something.
Well, that's great and all, and I think H told me something about that earlier, but how does that help me find my family?
Mouthy, aren't you? Well, you learned about the emission spectra, right?
Yeah.
The highest frequency on the spectra is the limit of convergence.
I remember that.
Whatever. Anyway, the energy shown here is the first ionization energy.
The what?
First ionization energy, the energy it takes to rip one of the outermost electrons away. The more electrons you take away, though, the more energy it takes. You can usually find out what group you're in and which house your family lives in with this. Because when successive ionization energy jumps happen, it either means you are losing an entire energy level or your electron configuration is becoming imbalanced.
I mean, I don't understand what half of that means, but...
First, this is basically everyone's ionization energies. The more protons you have, the greater the pull of the nucleus is, so it's harder to take electrons belonging to group 8 than it is to take electrons belonging to group 1. You got that?
Yes.
So you see, the dramatic drop from helium to lithium is because of this, but also because level 2 atoms require more energy than level 3 atoms. This is because the more levels you have, the more shielded by the lower levels an outer electron is from the nucleus's pull. So it takes less energy to take it away. This shows that there are main energy levels because of the drop in energy required because of increased shielding. Also, this is where these trends come from, where it goes down, then up, then down, then up, then down, then up.
Got it. The energy gets bigger going up and right. But why does boron and oxygen have a drop?
Well, that has to do with the electron configuration. Did you learn about that?
Yes.
You don't really look like you know what you're talking about, but I'll keep going anyway. It has to do with the electron distribution. So, this is the electron configuration of a boron atom. As you can see, there's 2 in this box and 2 in this box. And there's this lone electron right here because it has 5. It's easier to take away this electron because once you scribble it out, then there's an equal distribution in each box. This one just throws everything off, so it's easier to take it away to become more stable. You got that?
Yes. Yes, that makes sense. I get it.
Again, questionable, but I'm gonna keep going anyway. So oxygen is the same thing. As you can see, there's 2 electrons in 1s, 2 electrons in 2s, and then 4 in 2p. There it goes 1, 1, 1, and then there's this extra 1 in the first box. It's easier to take away this electron, this extra electron, so there's 1 electron in each box, and it's more equal. Please tell me you're listening.
Yes, I am listening.
I don't really believe you, but I don't actually care. So this explains for the discontinuities in the trends.
I know I say this a lot, but please tell me why this helps me find my family.
Well, we're within the same few protons, so you're definitely on the street somewhere. But knowing your ionization energy can tell you which group you're in.
Okay.
Their house, doofus. I just told you this. Now that the background information is taken care of, we can talk about successive ionization energy.
Energy jumps.
Yes, actually. If you keep taking away electrons, these successive ionization energies will continue to grow because there will be less electrons around to shield the outermost electrons from the nucleus. So, it'll feel a larger pull to the nucleus. This also accounts for large jumps in ionization energies, because if there's a large jump, it usually means you're dropping from one energy level to the other. So if you just count how many electrons you have to lose for there to be a large jump, you can find what group you're in.
How do you find that?
Don't worry, I have files on all of you. What were you again, kid?
Bismuth?
Bismuth?
Hey, you don't have to...
Anyway, I found it. This is all of your ionization energies. It shows the energy it takes to take away one of your outermost electrons. Yeah, you baby. I'm not gonna take nothing from you. Anyway, come here. Look at this. You see this massive jump between the 15th and the 16th energy? This is relatively the largest jump there is. So that means that after you take away 16 electrons, you're back to group 8. So if you just use a periodic table and you count, that means that you will be in group 15.
Oh. Are you sure this is right? I'm really tired of walking around a 2D table of a paper table.
We can always just do the math ourselves.
Okay. Why did you do that?
You wanted to know. I'm really just helping you out.
But,
Yeah, you're gonna want to shut up. Good. So, the equation to find your first ionization energy is E equals HV. E is the energy required. H is Planck's constant, which is 6.626 times 10 to the negative 34. And V is the frequency of light that is emitted when I give you this electron back. So here. Anyway, so
that's crazy.
that color, that frequency is probably 1.06 times 10 to the 39 meters. So, you get your handy dandy calculator, you multiply this out, and you get 702 kilojoules per mole. So, that means that your ionization energy is greater than TI's over there, but less than PO's, which is 2 houses that way. And it's definitely not my house. So your house is just right there.
You sat there and explained all this complicated magic stuff while my family was right over there?
What are you waiting on, kid?
Even I feel bad for him. You ain't gotta do all that leg.
Whatever. My life is dull as it is, and I didn't hear you telling him his family was next door.
Are you my family?
Ah, a new element.